Okay, on problem 1 here, it says there are more than 60% of university students covered by their parents' health insurance. Well, we're looking at, it's got 60% right there, and there's just one sample, university students. They either are or not covered there, so that's a one proportion z-test. That's D. So is there a linear relationship? The key word in there is linear. And of course those are quantitative variables. Car age, measure that in 1 year, 15 months, whatever. And maintenance cost, of course, cost, that's quantitative. But anyway, that's H, simple linear regression. Traffic accidents are counted sites before and after. And so we can count, that's a quantitative variable, and we can get the average of those differences. It's before and after. That's B. Is the average, so we've got the word average there. And of a textbook greater than $140, we're comparing one value, and to see if the mean is in this case greater than 140, that's option A. Is there a relationship between the type of healthcare coverage, which is qualitative? We're just going to put those into one of 3 categories, and job classification, which is another qualitative variable. That too has 3 categories. So that is a chi-square, F, relationship between 2 qualitative variables, at least one of which is multinomial. And then number 6, we're looking at percentage. And we want to know, they either do or do not have exercise facilities. Well, we have states east of the Mississippi. That's one group. And we have states west of the Mississippi River. That's a second group. So we're looking at percentages or proportions for 2 groups. That's E. It's the average. So, and deductible is a quantitative variable in different regions. So we have the average, and we have 4 groups. If we're looking at averages in 4 groups, that's an analysis of variance. Do more than 30%. So we've got percent, which is the same thing as a proportion of Russellville homes. That's one sample, just Russellville homes. That's our all Russellville homes would be our population. And then we take a sample from that. That's going to be our sample, but it's just one of them. So that is D, a one proportion z-test. And then average delivery time, I guess that's quantitative, how long it takes. 40 minutes, 48 minutes, 32 minutes. Well, this is actually ordered from Netflix, so this is going to be in days, 1 day, 2 days, 3 days. But the delivery time we're looking at, and we're looking at that for Netflix, and for another group, that is ones that are ordered from Blockbuster. That's 2 groups, and we're looking at averages, so that is a 2 sample t-test. And finally, we're looking at average time, and quantitative variable time, and we're looking at average on television over 12 minutes an hour. That's just one sample, so that is another moving down to the problems here. Daylight savings is a little more traumatic for me, I guess, than it is for the cat. But anyway, I can just leave that there. Might as well have it parked in. We've got before, 1 week before, and 1 week after, which you can see that in the table as well. And we have a quantitative variable, productivity. So this is a matched pairs t-test. But what we're going to do on the calculator here, we're going to get a 95% confidence interval, is just select staff, turn the calculator on, then select staff, and we're going to edit. And in list 1, we're just going to put the numbers that are in there. Press each number and hit enter. I actually can't do everything on my keypad, but I can do this on the keypad in my computer, so a little faster than As always, after you have all the numbers in your calculator, you should take a moment and make sure that you have everything correctly entered. And then I'm going to go over to the top of L3 and highlight that. And I'm going to want to subtract the after minus the before. So that's, I'm going to hit second and 2 for L2. See it put in the formula there. Subtract. Second L1. And we'll fill in here with the differences. So 72 minus 67 is 5, and so on. And so we want a 95% confidence interval. And we're just looking at the differences here. It's just one sample. So stat, tests. This is a t-test. We're going to get the sample standard deviation and enter. And remember at the top here, you get two options there, data and stats. And we're going to enter data. Our mu 0. Okay, let me go back here. This was what we would do if we were doing a hypothesis test. I'm going to go back and hit stat now and test. We just want a t interval. And so we're doing the data, but our list of data is in list 3. And leave the frequency thing around. It is 95% and calculate. So there's our interval. It's 0.51 to 7.5, and you can notice that, so that is the interval right up here. 0.51 to 7.49, and so that is our interval here. And part B says, does performance decrease? Now, keep in mind here, I did this really as to increase from before to after. If it looks like I did make the problem as good as I would like to have. Actually went up after. That's impossible. Okay, so I've actually made the numbers a little more realistic here. We want to know if we have our confidence interval and if it's decreased. Let's go back and look at that confidence interval. Stat, edit. And what I should have had was, you can see I changed that after and before. But generally speaking, productivity before was a little bit higher than it was after. So what I should have done here was before, which is second L2 minus second L1 or if I want to know if they went down, it should be second at 1 minus second L2 enter. Yeah, there we go. So in week 1, before it was 72, after it was 67, so there was a decrease of 5. I'm going to see if it's decreased really down here. And then if I do the interval, it's going to be stat tests t interval. Take R in less 3. You can see that goes from minus 749 to minus 0.51. Doesn't make any difference which order you put those in. So based on that 95% confidence interval, did performance decrease in the week after? And the answer is yes. And you know that because the entire interval is less than 0. So on number 2, it says, is there a linear relationship between number of days, that's quantitative, and employee performance, that's quantitative? And we want to use the stat feature whenever we can on this. So I'm going to write the hypotheses here. HR is, do this the easy way. There is a linear relationship between the two, and HO is going to be, there is not a linear relationship between the number of days after daylight savings and employee performance. So this is going to be a t-test. We're going to reject HO if t-test is greater than, degrees of freedom are 4, because there were 6 observations there, and minus 2. That's going to give us, if I'm not mistaken, 2.776. That's correct. 2.776. Or less than minus 2.776. So now is where we'll use our calculator and stat edit. I'm going to go over here and put the numbers in lists 4 and 5. Still have my numbers in there for the other one if I wanted to go back and check. And then hit stat again, or over to tests, and up to linear regression t-test. Some of your calculators have linear regression t-interval as well, but we're just doing the t-test, either one of them. And let's see, I had my x's in list 4, and I had my y's in list 5. don't change that. Leave that at not equal to. Don't put anything in there. Just hit calculate. And so we have a t-test of 6.70. Which is 6.7. Okay, that is 6.70 greater than 2.776. So we reject HL. Conclude that there is a linear relationship between the number of days after daylight savings and the time and employee performance. And the regression equation, back to my calculator. A was 12.06 and B was I'm sorry, I'm looking at my real calculator now. Let me go back to the calculator that I'm using here. Okay, so there's my A, 56.3, and arrow down one to get B, that's 1.31. So my regression equation, let's see, let's slow it moving. I don't know if I want to wait for that. So anyway, the regression equation, I'm going to put predicted, let me do it this way, performance predicted. Normally I would just put a hat over the performance to indicate that this is a predicted performance is equal to A, which is 56.3, plus B, which is 6.7, times, I'm just going to put number of days, this is the turnover. I should have put here just to give me a general form for the equation. And so that is your regression equation. And so if there are 5 days, you just plug 5 into that equation. Do that just on my regular calculator. 56.3 plus 6.7 times 5. I'll get 89.8. And then on Part E, forecasted performance, if it's 40 days after, and notice up here, our lowest number was 1, and our highest number was 22. And we should not be making forecasts outside that range. So our answer really is do not forecast. We are outside the range of X. This problem. Those of you who can type well are probably making fun of my slow typing now. That's life. Okay, down to number 3. Really lining up today. Okay, so we have a random sample of 100 males, 74. Says it takes over a week to recover, and 100 females, 66 takes over. So this is a qualitative variable. Does it take over a week or does it take over a week? But is the sample size large enough? Remember, with a qualitative variable, what we need is for all the yeses and nos. So 74, 100 minus that for the males. And for females, it's going to be 66, and 100 minus that, or 34. All are greater than 5. So yes, sample size is large enough. And our hypotheses, we want to know, is the population proportion of males higher than it is for females. So I'm going to put PA, A will be the males, greater than PB, that'll be our females, and HO will be PA equal to PB. And then we want to test using the p-value approach. And well, it says show the computations. That's awesome. That's a pretty good problem. Okay, but I'm going to just I'm going to do this with the calculator right now, and I will come back either using the stuff up at the school to work this by hand, or I might try something else here. But anyway, I'm going to do this with the calculator on here, and with the p-value, we're going to reject HO if the p-value is less than, in this case, 0.01. And I'm just going to use the calculator to get that p-value right now. And this is a two-proportion z-test. And in the first group, we had 74 yeses out of 100. The second group, 66 yeses out of 100. And this was, let me get down to the next one. Greater than, and calculate. And you can see that p-value was about 0.11. Therefore, we fail to reject HO. There may be no difference between population proportions. Better yet, we could say we do not have strong enough evidence population proportion of men is greater than of females in, say it takes over a week to recover. Okay, this one is a chi-square. And so the research hypothesis is that there is a relationship between demographic group and support for the continuation of the daylight savings changeover or fiasco, if you're in my corner on this. And so HO is there is up there, and there is a relationship between the two. And so we're going to do the critical value approach, and our degrees of freedom is equal to the number of rows minus 1 times the number of columns minus 1. That's equal to 4 minus 1, 2 minus 1, is equal to 3. So we are going to reject HO, get the chi-square test. Is greater than 7.82. Just read that off of the chi-square table. And then to compute this, I'm going to use, first of all, I'm going to put the values from this table into the matrix. And so I'm just going to arrow over to edit, hit enter, and I have a 4. Times 2 matrix. Now I can just put the numbers in there. You might note this would be a good one for me to ask by hand since each row adds up to 100. But anyway, once you have the numbers in the matrix, just hit stat again, tests, and arrow up to the chi-square test. Option C on this calculator. And just leave that alone, A and B. We put our observed values in A, and we'll let it put the expected in. Okay, so I got a chi-square test of about 2.5. That is not greater than 7.82. So we fail to reject HO. A not B. A relationship between the two. Okay, on this one, looking at the difference between two population means, the means for males and females. Is the sample size large enough? Well, NA is equal to 40, and NB is equal to 40. If they were unequal, just select the smaller of the two. So if it's 40, we're okay for skew, and okay for outliers, since we have at least 40. But N is not large enough. If there are extreme values. We're going to get a 95% confidence interval now. Calculator, and turn it on. This is, as I said, a 2-sample for T, doing an interval, so I'm going to go down to 2-sample T interval. And we're not inputting actual data now. If we did that, we would have to have 2 lists of 40 numbers each in our calculator, and we don't have that on this problem. But we are given the statistics straight away. So x bar 1 is 1.8 with a standard deviation of 1.6 and a sample size of 40. And then for the next group, for females, we had 1.1 and 1.4, also out of 40. Confidence level 95. We'll answer no to that, and we'll calculate. We'll get 0.03 to 1.37. Okay, this should say question there. Okay, so is the population mean higher for males than females? And the answer to that is yes, because the entire interval is greater than 0. So we're saying that they've lost somewhere between, I guess that's 0.03 of an hour to 1.37 of an hour. Okay, I'm not going to draw that right now, but hopefully you'll remember the thing where you had the bell curve and the true difference between proportions and then a collection of intervals. And that's a graph that I talked about in one class, but not in the night class. It really comes from a book that I used in a previous semester, so we'll skip that from now, or at least I don't expect you to know it, but I'll remind you that this represents Paris and Moscow, and this is Napoleon's march to Moscow, and the width of the line is the number of people that he left with. You can see that as he approached Moscow, the closer and closer he got, and the colder and colder it got, the more people, more soldiers that were, let's just say the fewer soldiers that he had, and then here's the black line is the return back. And by the time he got back to Paris, he had lost 44 out of every 45 soldiers that had left. Okay, on number 7, I'm just going to say this. This is the book that I read in the other class, so obviously you won't need to know that. But up here, just part A, it says discuss the role of box plots as they relate to what we've been doing in here, and include supporting graphs. I'm not going to write a whole answer out here, but basically, 2 things that you ought to talk about. One of those is the identification of outliers and extreme values. Of course, using SPSS, you would have circles for outliers and asterisks for extreme values. The other thing we used box plots for was to compare across groups with a multiple box plot. So when you have like a box plot where one group is males and the other one is females, then you can plot those both on one thing and look to see if it looks like there's a difference between the two. Central limit theorem, I hope you've kind of have the ideas there. You should go back and look in previous exams and reviews if not. I did want to go back and look at this one for a minute. This is from a PowerPoint that I gave you in class. And again, just on the left-hand side, let's just say on both sides, you have sample means of 10, 15, and 20. So in both of these examples, the sample means differ by the same amounts, but there's a lot less spread on the left example than the right. When you have less spread, it's easier to see distinct differences between the two groups. So on the left-hand side, there are distinct differences. You can see which group goes to which. But on the second side, there's so much variation and error in the data that you really can't tell a distinct difference between the 3 groups.